Thank you, Eric. Hello, everyone. My name is Dr. Christopher Galea, and as Eric mentioned, I'll be presenting to you on the longest title, High Efficiency Plasma Accommodating Radiofrequency Power Electronics for FRC Formation and Heating. Now, as noted, this is a very filled phrase. We will unpack these terms in this talk, and I'll be talking about our future plans in terms of getting to FRCs. But right now, we're primarily testing these things more in-house in company before an FRC. So this is a basic outline for the talk. We'll be going first over the background, which is on Starfire. This is a rotating magnetic field odd parity FRC based on the Princeton field reverse configuration. Our motivation is going to be radio frequency heated FRCs are requiring high efficiency plasma accommodating RF generators. So we'll go into that in a few slides. And our proposed solution will revolve around something called HARP, which is a high efficiency amplifier for RF plasma. And this will involve two main components. One is a solid state switch mode RF amplifier, which achieves very high efficiency. And then there's a reactance steering network, or RSN for short, which enables fast matching to plasma impedance changes. And so this can apply to a variety of technologies, and not just our particular FRC. We'll go over development progress, next steps, and a summary conclusion. So let's start with the background on Starfire, this RMF-not FRC. So Starfire is a fusion reactor concept based on the Princeton field reverse configuration. The key features include the odd parity rotating magnetic fields, which we'll go into in the next few slides. And these are responsible for both the current drive and heating. It's solely RMF heated and driven. And in fact, this is in the bottom left of this slide, we can see the PFRC2 device. There's an experiment at the Princeton Plasma Physics Lab. And in 2 talks from now, Lee and David will give a good amount of the updates on that experiment. The other aspects of this Starfire fusion reactor concept is its small reactor size. So we're talking more 2 meters diameter, 5 meters length, 1 to 10 megawatts per machine. So it's more for niche and kind of remote grid, off-grid type of applications. This is deuterium-3 fuel, where the tritium is quickly exhausted to minimize neutrons. And this is enabled by the small machine size. And lastly, we have a scrape-off layer flow, which extracts the energy and ash from the FRC fusion products. And that's illustrated in this bottom right figure, the Starfire closed-loop reactor schematic, where we have flow going from the source chamber. There's an FRC in a mirror, so it's flowing around the FRC, extracting both the energy and the ash, and then going out into an exhaust chamber and also exhaust handler. So let's go into a bit more on the odd parity rotating magnetic field. So in general, for rotating magnetic fields, we require phase independent currents, right? So we can think about 12 o'clock, 3 o'clock, 6, and then 9 o'clock, and that rotation of magnetic field. And this operates in the near field regime. We're not talking about a small wavelength. This is a large wavelength compared to the plasma size. And this enables a smaller FRC. Now, the odd parity RMF aspect has opposite magnetic field polarities across the midplane, right? So this is shown in the figure on the right. We can see that the arrows are pointing up, let's say on the right side of the machine, and then on the left side of the machine, we have the magnetic field pointing down. And so this is what we call odd parity. Now, initial research began with even parity RMFE. And in that case, you would have the arrows pointing up on both sides, and they would both rotate. Now, adding this field to the odd parity FRC ends up opening up the field lines, and this weakens particle confinement. Right? You can think of it that an FRC itself has an odd parity structure to it. It's on one side, the field is pointing a little bit more up, and then on the other side, it's pointing a little bit more down. And so the odd parity fields respect the FRC's topology better. So odd parity RMF, or RMF-not, was proposed to maintain closed field lines, and you can see quite a few of the references here. And this was to improve energy confinement for an RMF FRC. So lastly, about the background, I want to go into the key aspect of RMF-not, which is stochastic heating. And in this case, we can visualize this as RMF node antennas generating a rotating axial magnetic field at the midplane. So normally we think about these magnetic fields being, pointing in Y or X, but in the midplane you actually get this Z-pointed field from the RMF antenna. And because of this rotation of this field, you'll induce an azimuthal electric field, which is shown in the top right figure. So it's going counterclockwise in one half and then going clockwise in the other half, and that's going to rotate itself. Well, now along those lines, charged particles will freely accelerate, especially when we get into the field null region where there's zero magnetic field. And this results in this stochastic heating process. I actually show here an example of this with the bottom right figure, where electron energy is shown versus time for, let's say, one electron. And you can see that the electron goes through these spikes up and down as it gets caught in the counterclockwise and then clockwise loops of this electric field. But because of various collisions, you're going to get some changes in phase, and overall you're going to get this heating of the system, right? You're going to get a net heating, which is this average line under all the spikes. So ion heating has been demonstrated to deuterium helium-3 fusion temperatures, or predicted by the RMF node Hamiltonian code. It's a single particle code that's shown a lot of this predictions. And the key parameter range was shown to be basically where the RMF frequency is less than or about equal to this ion cyclotron frequency, and the RMF magnetic field is less than 1% of the axial magnetic field. And this is shown in these figures below, and the references go further into this. So let's now go into the motivation. Our motivation is for high efficiency RF generation with fast matching to FRC plasmas. So let's focus first on that term, high efficiency. Well, Starfire is a driven reactor. It's not self-heated. And this means that we need continuous power recycling for the RMF. We have to take that fusion power and keep putting it back. And in fact, that's shown here in an example power flow model that we have, a power flow diagram from our Journal of Fusion Energy paper 2 years back. And it shows that, let's say, for a certain amount of fusion power that you're producing, let's say here 2 megawatts, a good amount of power, a little less than a megawatt, is being fed back into the plasma for RF. So we want to make sure we have very high efficiency power electronics to be able to handle this type of heating. Current radio frequency heating systems use vacuum tube linear amplifiers, and these efficiencies tend to be below 50%. So hence there's this need for high efficiency RF generators in order to achieve the long sought engineering break-even. And that's also illustrated in this bottom right figure, where you can see this is from Entler 2015. And basically the engineering break-even threshold gets lower and lower as you get to a much higher loop conversion efficiency, right? So getting to a very high loop conversion, you're now getting to a much easier way to get to break-even. And then lastly, in the motivation, we want to talk about fast matching to the RF plasma. So FRC plasma formation and instabilities tend to lead to impedance variations on the microsecond timescales. And that was even shown in quite a few of the talks earlier today that we talked about many things on microsecond times. Now, these are some examples from recent PFRC2 data and experiments, where we show in the densification stage of the FRC that there's a fast densification that's around 7 microseconds in this case, and generally is kind of on the microsecond timescale. And in fact, this ends up resulting, if you see in the figure on the right, that the percent power reflected drops really quickly as you get past the densification stage. So you're dealing with these very variable and changing loads, and you want to be able to handle those with your electronics. So these reflections can damage components and also weaken plasma coupling. So hence we emphasize the need for fast matching to handle plasma mismatches in real time. And if we compare, with what's usually used is a tunable matching network, but that can handle only down to around millisecond time. So you're very limited in terms of what you can do there, even if you use like electronic control. And so we really want to get down to the microsecond time scale. And with this, we want to enable efficient plasma coupling over the whole operational envelope. We don't want to just wait till the plasma turns on and then now we have some matching. We want to see if we can match over that full startup and shutdown, which ends up having a big effect on the total efficiency. So this is a proposed solution, high efficiency plasma accommodating RF amplifiers, or we made our own acronym of HARP, which is high efficiency amplifier for RF plasma. So this is composed of two main parts, the solid state switch mode RF amplifiers and the reactant steering network. So let's start with number one, the solid state switch mode RF amplifiers. So these are either, examples are Class D or Class E amplifiers. The key aspect of these amplifiers is that ideally their efficiencies get up to 100%. And I'll go into the next slide about why, the intuition for that. These are enabled with wide bandgap semiconductor device technologies. So for instance, gallium nitride is one that we've been using a lot recently. There's also silicon carbide and other ones. And these enable higher voltages, efficiencies, and frequencies to really start getting into that fusion relevant technology. So just to give a little more intuition as to why this is so high efficiency, the Class E is essentially shaping the transistor drain voltage, VFT, and the current waveform, IFT, in order to minimize their overlap. And we think about the power dissipation in a transistor as just the integral of V times I. So if we're able to minimize that overlap between them in time, we're basically making that dissipation go to zero. And that's even illustrated in this little circuit model that I show here, where the VFT is the green, and then the IFT is the red, and you can see that there's very little overlap. And these result in a nice RF signal, the nice sinusoid, that's blue. The other part of the proposed solution is the reactant steering network, RSN. So this is two amplifier branches that share power according to load impedance and two control knobs, the voltage ratio and the phase difference. The key thing we're trying to do here is ensure that there's zero voltage switching to maintain that high efficiency Class C operation. And this is shown as an example in the figure on the right, where by shifting the phase between these two branches by 164 degrees, in this case, we're able to get this nice smooth roll off for both of the signals. And that increases efficiency versus if you just put them in together without any kind of phase difference. And I want to emphasize this here that if we could use, let's say, a field programmable gate array, and we can enable digital control that would be able to get us to these type of fast microsecond timescales for time-varying plasma load impedance control. So that's really what our end goal with this type of control part of our work. And lastly, I'll just emphasize before we go into some of the recent work that frequencies have been demonstrated from the hundreds of kilohertz to tens of megahertz, and this is relevant to a variety of RF plasma heating systems. So our development progress, first with the 27 megahertz board, we've demonstrated up to 90% efficiency, high efficiency Class C operation. That's including the nice zero voltage switching that we get in the yellow approximately. And we found that there's some dependence on the transistor and the operating voltage that ends up limiting some of the very low power stuff. You might get lower efficiency because you're using a higher power FET. So that will come into play in some of the next few slides. But if we use a lower power FET, we can get to 90% efficiency easily. This is just another note here that we've been exploring with various inductors and trying to optimize the system. And so even just this one case of a slightly larger hand-wound inductor resulted in twice the current going through this, and we can get to a higher power for the same board. So now going on to the reactant steering network, this is we now have pushed the state-of-the-art of reactant steering to 27 megahertz. The previous state-of-the-art was 13 megahertz. And this incorporates two Class E boards in parallel, essentially. And this frequency is kind of in the higher end of various heating ranges that are considered, for instance, by TAE and others. This uses a resistor-inductor load representing an inductively coupled plasma, and that's shown here in the bottom left figure. So our experiments capture the key trends from simulations. If we use these two terms, so the voltage ratio we'll call KLC, and then the phase difference we'll call delta LC. We first show a baseline case where the amplitude ratio is 1, while there's no phase difference, delta is 0. And this results in a pretty low efficiency. What I want to note here, though, is that we do end up capturing in the experiments pretty well with our simulations. And so, right, the red curve corresponds to this right picture, and then the left curve corresponds to this left picture. That's the blue curve. And now, note that it had to be a small change in the inductance, but that's likely due to the stray inductances in this plasma, or in this load. But now, if we change the phase difference now to a minus 45 degrees, we increase efficiency quite a bit. This is already a 20% increase in efficiency, also with good agreement with our simulation experiment. And I'll note here that this could be an even higher efficiency. This was, as I mentioned, we were using still these higher power FETs that were not really optimized for this voltage setting. So this could be well into like the high 80s efficiency. Another part of our development progress is plasma circuit modeling. Right? So we've created a plasma circuit simulation by implementing an ICP model into QSpice. An ICP example is shown on the right, and you can see that it has some similarity of a cylindrical plasma, something to start with for reference. Now, the key reason we start with an ICP prior to an FRC is because there are these nice, simple, closed-form solutions that exist for the plasma impedance. So it makes it an easier start case to go into and verify our simulations and our control. This informed our choice of the resistor-inductor load that I use in this circuit test. And in the figure on the bottom left, we show exactly that, those type of the resistance of the plasma and inductance of the plasma for an ICP, and how we're able to easily capture that in our model as well. So it's quite a nice closed-form solutions that we now have in our own MATLAB models. So this generates an equivalent plasma circuit for optimizing amplifier design, and we can utilize this for testing our control of various plasma loads. So the last main development progress I want to go over is power combining. So the key question we were asking here is, as we scale up in power, how do we combine circuits with reactive steering networks? Well, we considered two main topologies. So one is a tree of RSNs. Basically, this is one RSN here. There's capacitors and inductor kind of in parallel. And then each of those is going to feed into another RSN. So it's kind of that's the tree network going on there. And then a parallel combined RSN is going to have the reactive steering network on right, but then the two class E's will be connected in parallel to one branch, and then the other two will be connected in parallel to the other branch. And so we tested these with two different static loads to check how well the RSN can adjust to both of these cases. So we found that the case 2 had the highest efficiency and smoothest waveform across the board. And in fact, it was also much simpler to scale up. You can basically do any 2n number of boards instead of having to do 2 to the n power, which the other one was more limited by. So I just want to go over some next steps as we increment this work forward. We're currently developing a benchtop ICP plasma to test our HARP system on a plasma load. In fact, this is, I really just designed this board and printed it. It's right here. This is our little coil and a small neon tube. And this is it glowing near a little plasma discharge. And we also want to develop that real-time control capability to handle plasma load variations. So having this benchtop setup allows us to do things very quickly and test a lot all at once. We also plan to scale up RF to fusion relevant powers. So the first stage would be 1 to 10 kilowatts, And then it would be to the hundreds of kilowatts to megawatt is kind of the ultimate goal there. We've increased the frequency, we want to increase frequency to about 150 megahertz, which is relevant to high field reactors. But now this will require FETs with RF optimized packaging. And lastly, we want to test the HARP system on the next machine, Starfire 1. So this is going to be expounded on in Leila's talk right after mine. And this is a subscale reactor where we want to demonstrate and optimize the RMF not heating. We're really aiming for that 10 keV in this reasonably small reactor, experiment. The RMF frequency would be about 1 megahertz, and the power would get up to 300 kilowatts. We also want to develop HARP control from plasma impedance measurements and hybrid PIC modeling. So in summary, this is a solely RMF not heated FRC that requires high efficiency and a rapid adjustment to plasma loads. The HARP system shows promise, combining a Class E amplifier and RSN. We have some initial tests of power that demonstrate key features of this technology. And we have a benchtop ICP test that's underway in order to verify HARP on an actual plasma load. So I want to thank you for our Japanese audience. Goseichou arigatou gozaimashita. Thank you for your time. And we have some RF power electronics. Actually, we have our first board online as well as demo board, and we have some upcoming releases that we'd like to release at some point. Thank you.
Thank you.